Hello and welcome. In this session 5.3, we will learn how to perform compression tests on local materials. It includes uniaxial compression and triaxial compression. Session 5.3a is on uniaxial compression tests. Uniaxial compression test is perhaps the most important and the most commonly performed test on local materials. It is equivalent to the cube strength test for concrete. You therefore would expect some test standard or guidelines. And yes, the International Society for Local Mechanics has set out the suggested methods for uniaxial compression tests, as listed here. We will again follow the ISM suggested method in describing our test to determining the uniaxial compressive strength of local materials. Compression test is to be performed on a compression machine. The compression machine is a loading machine providing axial compressive load of large loading capacity sufficient to break the rock. Because of relatively high strength of rock, the machine should be strong and stiff. Usually, the loading should be controlled either manually or more advanced by servo controller. Specimens for testing need to be properly assembled with measuring sensors to ensure the specimen is loaded properly and the load and deformations are measured. We'll elaborate the specimen assembly in the next slide in more details. Then, of course, there must be a data acquisition and control system. This is to record the measurements on load and deformations and to control the loading. We will cover more details again on servo control system later. In the ISM suggested method, there is quite strict requirement on local specimen assembly, particularly on spherical seating. Local specimens are typically rock cores cut into cylinder with length 2 to 3 times the diameter. For example, if the core diameter is 50, the length should be 100 to 150 millimeter. The specimen should be sandwiched between hardened steel platens. The steel platens should have spherical seating. The spherical seating is to ensure uniform loading on the specimen in case the specimen ends are not parallel. We will need to measure deformation of the specimen during loading in order to calculate the Young's modulus and the Poisson's ratio. Therefore, there should be measuring sensors for axial and lateral displacements by either strain gauges or LVDTs. We will explain a bit more details on how to use strain gauges and LVDTs devices in the next slide. Measuring the axial loading is usually by load cell and it is normally built in the compression machine. If not, then a load cell should be attached to the specimen assembly for axial load measurements. If strain gauges are used for specimen deformation measurements, then the strain gauges must be glued on the specimen surface at mid-height. Usually, we need minimum 2 sets of strain gauges to be on the opposite side of the cylinder. The upper right figure shows the strain gauges glued on the rock surface in the middle of specimen cylinder. The vertical gauge measure axial strains, and the horizontal strain gauges are for lateral or radial strains. You should have another set of strain gauges glued on the same way on the other side of the specimen cylinder at the middle height. You can attach more strain gauges, then they should be spaced equally. If you only want to measure axial strain, that means you will only be able to calculate the Young's modulus, but not the Poisson's ratio, then you can attach only the vertical strain gauge. You still need to glue at least 2 on opposite sides. Another common device for deformation measurement is LVDT. The middle right photo shows the axial displacement extensometer. It measures the axial displacements between the pair of legs, which are on sides of the specimen. The lower right photo is the circumferential displacement extensometer. It is a chain device around the specimen circumference at the middle height and it measures the whole circumferential displacement. Both devices use LVDTs for actual measurements with accuracy in the order of micrometers. Modern compression machines are equipped with servo-controlled loading system. The servo-controlled loading system uses a measurement, load or displacement, as a feedback to inform and to control the hydraulic loading system to increase or decrease the loading in order to maintain the prescribed values in the feedback control loop. The typical arrangement of servo control is illustrated in the figure here. Feedback measurements can be axial load, axial strain, or diametrical strain. Based on the feedback signals, the controller will make adjustment to close the gap between the current value and the desired value, sending the control to the servo valve that in turn controls the loading. Through this closed loop, the loading is expected to adjust by increasing or decreasing to ensure the feedback measurement follows closely the prescribed or desired value. For example, if we want to make sure the specimen with continuing axial strain of 5 micron per second. The feedback signal will be the axial strain measurement. Axial strain measurements are fed to the control system by comparing the current value of the strain and the prescribed desired value of the strain. Then order is sent to the servo valve to apply the loading to the next level of strain. Servo control system with a high loop closure rate of at least 1 kHz in real time are recommended for lock testing. Now let us start with specimen preparation. You should select the specimen carefully to make sure the specimen for testing are intact, homogeneous, and no visible defects. If you are selecting the specimen from rock cores, make sure you select the portion of cores to cut for testing are good, solid, and intact, with no cracks and no other discontinuity features. Usually, specimens are cut from cores. Sometimes, specimen can also be cored from a rock block. The specimen should be right circular cylinder with diameter preferably of not less than 50 mm and the height to diameter ratio of 2 to 3. Rocks such as granite has minerals of coarse grains. The diameter should be at least 5 times the maximum grain size. The two ends of the specimen must be cut and grinded to be flat, smooth, parallel, and perpendicular to the specimen axis. The sides of the specimen should be smooth and straight within 0.3 mm tolerance, and there should be no visible irregularities such as the void and the pores. To start the test, make sure you measure and record the specimen dimensions, densities, and water content conditions. In terms of dimensions, you will need to measure the diameter and the lenses several times on different locations. For example, diameters at different height of the specimen. Water content should be recorded as room dry, saturated, or natural condition. Attach the axial and electrical strain gauge measurement devices to the specimen as we have learned on slide 5. Placing the specimen assembly as shown in slide 4 in the compression machine, centered with the axial loading piston. Then we can start applying axial load to the specimen assembly continuously at a constant stress rate of 0.5 to 1 megapascal per second, or to make sure it will reach failure in 5 to 10 minutes. While we apply loading, record load and stress and displacement or strain measurements at 1 Hz frequency. Stop the test after failure or after the peak stress. If the test is not planned to perform or to obtain post-peak stress strain curve, for tests to obtain post-peak stress strain curve, we will explain the procedure on the next slide. Number of specimens tested should preferably be at least 5, or with practical considerations. You can skip slide 9 and slide 10 if you are not interested in obtaining post-peak stress strain curve. In most engineering applications, design parameters only require peak strength, Young's modulus, and the Poisson's ratio. The procedure to obtain post-peak stress strain curve requires a servo-controlled loading machine with the feedback channels from axial load, axial strain, and the circumferential strain. Again, specimen and the specimen assembly with strain measurements are positioned in the servo-controlled loading machine. We start with using axial load as a feedback control to apply an initial axial stress to approximately 10% of the peak strength. Log specimen now is in the elastic behavior region. We now change the feedback control to axial strain control and set the axial strain rate at 0.001 per second. The machine will continue to apply loading to the specimen according to the prescribed feedback rate. Let the loading to continue to approximately 70% of the peak strength. The rock is now perhaps about to pass the elastic and to start yield. We then change the feedback axial strain rate to 0.00001 per second. To apply the load slowly and gently to the specimen, get about to yield and to reach the peak and fail. The reason to apply slow axial load is to control the load to avoid sudden and violent failure of the rock we usually observed in normal testing. With the slow loading controlled by the axial strain rate, you will observe, in fact, the axial load decreases after passing the peak. Continue to let the axial load to decrease to approximately 50% of the peak strength. Then we change the feedback axial strain rate back to 0.001 per second to increase the test speed. We usually stop the test when the axial load reaches about 30 to 40% of the peak strength. Throughout the test, measurements on load and displacements or strains are recorded at 1 Hz frequency. From those recorded measurements, you can generate by the computer the complete stress strain curves, including the post-peak part. The procedure outlined on slide 9 is for most of the rocks. However, we have observed some crystalline rocks have extremely brittle behavior, which we call class 2 behavior. You can read about class 2 behavior in some textbooks on rock mechanics. For rocks potentially exhibit class 2 behavior, we'll use a test procedure outlined on this slide to obtain the post-peak stress-strain curve. The difference from the test procedure in this slide from the last slide is step C. Instead of continuing using axial strain as the feedback control with a lowering strain rate, here we change the feedback control to circumferential strain and set the strain rate at 0.0001 per second. Again, following the feedback control, axial load will increase slowly to the peak and then decrease after passing the peak. Continue to let the axial load to decrease to approximately 50% of the peak strength. Then switch back the feedback control to axial strain control at 0.001% per second, as we did in the last slide. As we mentioned earlier, during the test, measurements on load or stress, axial and lateral strains or displacements are recorded at a frequency of 1 Hz by the computer data recording system. The computer will easily generate the axial stress, axial strain curve from the recorded data. You can ask the computer to produce a linear curve through the data regression, which will make the curve easier to see and analyze. You can get the uniaxial compressive strength and the Young's modulus from this axis stress axial strain curve. The computer can also plot for the axial stress lateral strain curve. You can calculate the Poisson ratio as a ratio of the tangents of axial stress axial strain curve to the axial stress lateral strain curve. We usually calculate the Young's modulus and the Poisson ratio at 50% of the peak strength, which ensures the rock is in the elastic region. Here are the typical and the usual axial stress axial strain curve and axial stress lateral strain curve. From the curves, graphically, we can easily determine the peak stress, which is the uniaxial compressive strength. The Young's modulus is a tangent of the axial stress axial strain curve at the 50% of stress level, as shown on the right side. From the axial stress lateral or circumferential strain, you can also get the tangent of curve at the 50% stress level on the left. Poisson's ratio is a ratio of the tangent on the right to the tangent on the left. Typical and a common complete stress strain curve, including post-peak part, is shown here. The additional information provided by this complete stress strain curve are the post-peak stress strain relationship, the residual strength, and the local modulus at a stress level after peak strength or after failure. The unloading and reloading can be set in the feedback control during the post-peak testing. To report the uniaxial compression tests and the uniaxial compressive strength, the following information should be included in the report. A. Log sample information, including lithological descriptions, grain size, rock anisotropy, sample locations and depths, sampling date and the method, storage history and the environment. B. Specimen information, such as number of specimen, methods of specimen preparation, measurements of size, and water content observations. C. Date of testing and the test duration, number of specimens tested, machine information, test procedure, that including descriptions of loading control. D. Values of applied force, stress, and the strain as tabulated results or as recorded on a chart. Stress strain curve generated or plotted by the computer from the recorded data. E. Uniaxial strength, Young's modulus and the Poisson ratio at the 50% of stress level, the average values and also the range of those strengths, modulus, and the Poisson ratio. F. Mode of failure, whether is axial splitting or shear failure, and also the observed shear plane angle. G. Photos of specimen before testing and the failed specimen after testing, as well as the compression machines and specimen assembly. Triaxial compression tests are similar to uniaxial compression tests, but with additional confining circumferential stress. This is to measure the rock strength on the ground, which is subject to in situ confining stresses. The test method for triaxial compression tests is documented in this ISM suggested method for determining the strength of rock materials in triaxial compression, published in 1978. Equipment required for triaxial compression tests are very much similar or the same as for the uniaxial compression test, except there is an additional triaxial cell in which a confining pressure is applied to the rock specimen. The typical test system is shown on the right. Again, you can see the compression machine with a thick and stiff frame. You can also see the triaxial cell in the center of the compression machine. Test specimen assembly is inside the triaxial cell. We'll explain the triaxial cell in more detail in the next slide. Through the cell, Confining pressure is applied, commonly by hydraulic compressed oil. The test system is linked with data acquisition and control system, similar to that of uniaxial compression. It can also have a servo control system for the triaxial compression test. Let us examine the triaxial cell assembly in details in order to understand how it works. The drawing on the right is a commonly used triaxial cell, developed by Hook and Franklin, now commonly called the Hook cell. The specimen assembly inside is the same as in uniaxial compression, with spherical seated platens and strain gauges. The specimen assembly is confined by rubber sealing sleeve around the circumference and sealed inside the triaxial cell. Oil is injected into the cell through the oil inlet, filling the gap between the cell body and the rubber sleeve. The oil pressure on the rubber sleeve is transmitted to the specimen as a confining pressure. As a triaxial cell has the similar working principles. The rock specimen assembly is sealed by usually rubber sleeve or jacket inside the triaxial cell. The triaxial cell is then filled and pressurized with oil to generate confining pressure. Some advanced triaxial cells can incorporate heat devices and testing the rock specimen at elevated temperature. Specimen preparation for triaxial compression tests is the same as that for uniaxial compression tests. It is prepared into circular cylindrical shape. For using the Hook cell, the commercially available cells are either in 38 mm or 50 mm. So the rock specimens are about in 38 mm or in 50 mm diameter in order to fit in the rubber sealing sleeve shown on the far right in the photo. The length of the specimen cylinder is 2 times the diameter. Testing procedure described here is using the Hook cell. First, we need to measure and record the specimen diameter and length a few times at different height and size. Then measure the weight and record the water content condition. Attach the axial and lateral strain gauges to the specimen. Place the specimen into the rubber sleeve and the triaxial cell. Attach steel platens to the specimen, then place the triaxial assembly in the compression machine, centered with the axial loading piston. Connect strain gauge wires to the data logger. We first apply a small axial load to the specimen assembly. This is to fix the triaxial assembly in place and not moving around while pressurizing the triaxial cell. Then we apply axial load and the confining pressure slowly and simultaneously to ensure axial stress is always slightly higher than confining pressure until confining pressure reaches the prescribed pressure value. Then we continue to apply axial load to the specimen at a constant stress rate of 0.5 to 1 megapascal per second, or to fill the rock in 5 to 10 minutes. Throughout the axial loading, confining pressure in the triaxial shell should be maintained within 2% of the prescribed value. While loading, record load or stress and displacement or strain measurements at 1 Hz frequency. If post-peak stress strain is to be obtained from test, you can use the same approach as in the uniaxial compression test for the post-peak test with servo-controlled loading system. For other types of triaxial cell, you need to follow the instructions on the specimen assembly in the triaxial cell. Make sure sample seating, cell seating, and the sensor connection. While applying the confining pressure, always make sure that the axial stress is greater than the confining pressure. During testing, axial load, confining pressure, axial and lateral strain are recorded at a frequency of 1 Hz by the computer data recording system. You can generate the axial stress, axial strain curve from the recorded data. From the curve, the triaxial compressive strength and the Young's modulus can be determined. You can also generate the axial stress, lateral strain curve. Together with the axial stress, axial strain curve, you can calculate the Poisson's ratio as a ratio of tangents of axial strain curve to the lateral strain curve. It is recommended to calculate the Young's modulus and the Poisson ratio at 50% of the peak strength. The pre-peak axial stress, axial strain curve and axial stress, lateral strain curve of a triaxial compression test is similar to that of a uniaxial compression test. From those curves, we can graphically determine the triaxial compressive strength at a fixed confining pressure. The Young's modulus is the tangent of the axial stress, axial strain curve at the 50% stress level, as shown on the right side. The Poisson ratio is the ratio of the tangent of axial strain curve to the tangent of lateral strain curve. With tests done for the same sample at different confining pressures, we can plot axial stress, axial strain curves together. The figures shown here is a typical set of axial stress, axial strain curves at different confining pressures. With those stress strain curves, we can analyze the change behavior with increasing confining pressure. This was discussed in session 2.2 in rocket mechanics principle course earlier. Experimental report on triaxial compression tests should cover the following aspects and informations. A. Log sample information, including log type, and lithology, grain size, anisotropy, sampling location and depth, method, and date, and storage information. B. Specimen descriptions and measurements, including number of specimens, method of specimen preparation, diameters and lengths, and water content conditions. C. Test date and duration, number of specimens tested, machine information, testing procedure, including descriptions on axial stress and confining pressure loading procedure and control. D. Data and graphs from the tests, such as recorded stress and strain data, stress strain curves generated by or plotted by the computer from the recorded data. E. Tabulated results on triaxial strengths, Young modulus, and the Poisson ratio, generally at 50% of the strengths, with confining pressure, including average values and ranges. F. Mode of failure, whether the failure is axial splitting or by shear failure, and the measured shear plane angle. G. Photographs of the specimen prepared and the specimen after failure, as well as the compression machines and the triaxial specimen assembly. The main objectives of determining uniaxial and triaxial compressive stresses are to obtain the stresses at a specific stress condition, and more importantly, to construct a stress criterion for design and modeling. This session 5.3c is to illustrate how to determine the parameters of strength criteria used in rock mechanics and rock engineering. We will use the uniaxial and the triaxial compressive strength results obtained from the tests to derive the parameters for the Moore-Coulomb strength criterion and the Hooke-Brown strength criterion. The method used to determine the strength parameters are quite simple, by plotting the Moore circles and doing the regression analysis. For the Moore-Coulomb strength criterion, what we need to determine is the cohesion C and the internal friction angle phi. First, we plot the triaxial and uniaxial compressive strengths by the Moore circles and draw the best fitting tangent straight line to represent the Moore-Coulomb strength envelope. From the strength envelope, we can find the cohesion C and the internal friction angle phi for the Moore-Coulomb strength equation. We learned in session 2.5 that the Moore-Coulomb equation gives much higher tensile strength. Therefore, we use the actual tensile strength obtained from the test as the cutoff for the strength envelope on tension. Here is the illustration on how to determine the cohesion C and the internal friction angle phi, as just explained with the last slide. The semicircles on the right side of the vertical axis are the Mohr circles drawn using each pair of confining pressure sigma 3 and the corresponding strength sigma 1. Then we have to draw a straight line as the best fitting tangent to all the Mohr circles. This straight line is the Mohr-Coulomb strength criteria envelope. The intersection of the line on the vertical axis is the cohesion C, and the tangent angle of the line is the internal friction angle phi. The Mohr-Coulomb strength envelope is a cutoff to the tensile strength determined from the test, or to the value of 10% of the uniaxial compressive strength. With C and phi, we can determine the strength of the rock material at any confining pressure using the Mohr-Coulomb strength equation. We can also determine the parameters for the Hooke-Brown strength criteria. Again, we draw the Mohr circles using the uniaxial and the triaxial compressive strengths and the tensile strength from the tests. And then draw the best smooth touching curve to represent the Hooke-Brown strength envelope. For each set of sigma 3 and sigma 1 from the test, using the Hooke-Brown equation, sigma 1 equal to sigma 3 plus m sigma c sigma 3 plus sigma 3 squared, and then the square root. With the value of sigma c obtained from the test, we can calculate parameter m for each set of sigma 3 and sigma 1. We will obtain a series of m values, and the mean value of those m is used for the Hooke-Brown equation. Again, the plot of Mohr circles and the drawing of the tangent curve is shown on this slide. The tangent curve is the Hooke-Brown strength envelope. As we have learned in session 2.7, the Hooke-Brown strength envelope is a curve. You may wish to revisit session 2.5 and 2.7 on the Mohr-Coulomb strength criteria and the Hooke-Brown strength criteria in combining with the exercise here. I'm ending this session here. Goodbye and see you at the next session.